Hi, this is Tzvi Rosen. In this video, we're going to talk about a genre of problem that comes up on a lot of algebra qualifying exams, and that is, given that the order of G is n, prove that the group G is not simple. Okay, you'll recall that being simple means you have no normal subgroups except for the trivial subgroup and the whole group. Okay, and here are the steps to this problem. First, you factor n down into its primes. People make enough mistakes in this that you should pay attention to make sure you do it correctly. Next up, you apply Sylow's theorems to find all possible values of NP. Then, using those different options for NP, you count the elements of each order in your group. Okay, that might lead you already to understand that your group has a normal subgroup. Next up, if you haven't figured out yet that your group is not simple, you can consider group actions, which induce homomorphisms from your group to a permutation group. And finally, if things really are complicated, then you can consider intersections of Sylow P subgroups and their normalizers. Okay, so let's talk a little bit more about each of these steps. The first step doesn't need any more explanation, just make sure you do it carefully. For step 2, we want to apply Sylow's theorems, so let's review those. So Sylow's theorems apply to a case where you have the order of the group is equal to a power of p times m, where m is relatively prime to p. And then the set of Sylow p subgroups are the set of H subgroup of G, such that the order of H is equal to p to the alpha. So it's that highest power of p that appears in the factorization of G. Okay, and the number NP denotes the size of the set of Sylow subgroups for the prime p. Okay, so the first Sylow theorem says that you always have a Sylow p subgroup. Okay, so, or rather, let's put it this way, for any p, the Sylow p subgroups is non-empty. Okay, so we should always be able to look at those. Sylow 2 states that if you have two distinct Sylow p subgroups, so p and q in the set of Sylow p subgroups, then you should find a group element such that p is the conjugate of q under that group element. Okay? So this tells you that all of the Sylow p subgroups are related to each other by the action of conjugation. Let's just give ourselves a bit of space. Okay. And Sylow 3 states that NP is congruent to 1 mod p, and furthermore that NP is equal to the index in G of the normalizer of P, where P is one of the Sylow p subgroups. For P in Sylow, in the set of Sylow p subgroups, so it doesn't matter which one, just any one of them, take its normalizer, and NP will be the index of that subgroup in G. Okay, as a corollary of that, NP is going to divide the order of the group. Okay, and we're going to use all of that information as we analyze the possible values of NP. Okay, as for counting elements of each order, when I have some collection of Sylow P subgroups, and they each have size P, then they're all going to intersect trivially, because their intersection is going to be a subgroup. And since the two Sylow P subgroups are distinct, they can't just be identical. So their intersection is going to be the identity. So you know that given a set of 10 Sylow 7 subgroups, you have 6 non-identity elements in each of those 10 subgroups. And so you're going to have 60 unique elements of order 7 there. The idea being you can count all elements of order P precisely. On the other hand, when P and Q in the Sylow P subgroup have higher powers of P as their order, things will be more complicated. You don't know how they will necessarily intersect. But we'll get back to that more a bit later. And the next step was defining a group action. So when you have a Sylow P subgroup, we can talk about 2 important group actions and their induced homomorphisms to permutation groups. So the first group action is G acting on the set of Sylow P subgroups. Okay, and there you just conjugate each Sylow P subgroup that returns a different Sylow P subgroup. The other action is left multiplication, and here you're not acting on the set of Sylow P subgroups, you're acting on the set of cosets of P, a specific Sylow P subgroup. And the action there is by left multiplication, so that you just multiply every element of the coset by some G on the left. That gives you a different coset. And the kernels are normal subgroups of G. So again, these actions define homomorphisms to permutation groups, and their kernels would be normal subgroups because that's always the case. And what this means is that if G is a simple group, the kernel must be 1, just the trivial subgroup, or the full group. And then by following that train of thought, you can lead to some contradiction, which will tell you that no, the group can't be simple. Okay, so let's say you tried all of these different approaches and you still haven't gotten anywhere. Then you can backtrack to counting orders of elements. And even though it's complicated when you're looking at higher powers of P, you can still analyze by cases. Okay, so in the case where P squared divides the order of your group, so counting elements of each order was complicated, you can analyze cases. First case, all Sylow P subgroups intersect trivially. And in that case, you can try counting elements of order P to the K, since they'll still be unique, right? They're not, these subgroups do not intersect at all. The second case is where they intersect non-trivially. And then you can look at their intersection. What does the intersection of those two groups look like? So for instance, if we're looking at 2 Sylow P subgroups of size P squared, then their non-trivial intersection will be of order P. And then we can look at the normalizer of that subgroup and the index of the normalizer of that subgroup. Maybe we can define a group action involving that normalizer. Okay? But again, this is kind of worst case in terms of an exam question, though it comes up a lot for trickier orders of groups. Okay, so let's start with a simple example. We're looking at 200, and so as with every example, we start by taking the prime factorization. So 200 equals, well, we can pull out a 2 and get 100, another 2 gives us 50, another 2 gives us 25. So we have 2 cubed times 5 squared. Okay. So in terms of Sylow's theorem, let's look at our sizes of sets of Sylow P subgroups. So we'll look at N2 first. We know that N2 is congruent to 1 mod 2. And because N2 divides the group order, it's going to divide 5 squared. Okay, so you can disregard the 2 cubed because we know that it's 1 mod 2. Okay, so what does that mean for us? That tells us that N2 could be equal to 1. it could be equal to 5, and it could be equal to 25. Right? These are all factors of 5 squared, and they're all 1 modulo 2. How about n5? Well, we know this is, again, congruent to 1 mod 5, and must divide 2 cubed. So that tells us that n5 has to be in the set 1. And now we can look at other possible values of n that are 1 mod 5. So things like 6 and 11 and 16, 21. So these are all of the integers that are 1 mod 5, but none of these divide 8, right? So you can immediately ignore these and conclude that n5 is 1. And when we have a unique Sylow P subgroup, that tells us it's normal. So G is not simple. Okay? And so we can bid the example of 200 adieu and move on to the next example. Let's consider 80. So the first thing we do is prime factorization, as always. 80 equals 2 times 40, it's 8 times 10, 16 times 5. Okay, so 2 times 2 to the 4th times 5. Okay. Now let's consider the different values for np for our 2 primes. We have n2 and n5. So n2 is going to be congruent to 1 mod 2, and it's going to divide the order of the group, which means in this case that it has to divide 5. But for us, that means that n2 will be in the set 1 or 5. Okay. Those are the only factors of 5, and they are both 1 mod 2. Okay, as for n5, we know this is going to be 1 mod 5, and we know it's going to divide 2 to the 4th, okay, which is 16. Okay, so for what does that mean for us? Well, n5 would have to be either 1, okay, 6 doesn't make it in, 11 doesn't make it in, 16 is possible because it's 1 mod 5, and it's a divisor of 16. Okay, so this doesn't tell us right away that G can't be simple. Okay, so it could be the case we could have possibly 5 Sylow 2 subgroups and 16 Sylow 5 subgroups. Okay, so we can't yet come to the conclusion that we have a normal Sylow P subgroup. So what do we do next? We count elements of each order. So I know that if I were to look at the Sylow 2 subgroups in the group of order 80, these would have size 16. Two to the 4th. So in particular, they can intersect each other in unpredictable ways. So let's focus on the Sylow 5 subgroups. Okay, so just make a note that it's complicated. Looking at the Sylow 5 subgroups, these all have cardinality 5. Okay, so if I wanted to count all of the elements, of order 5, I would simply take 5 minus 1 times n5. Okay, looking back, that had to be 16 if we're not taking 1. Okay, so again, this is non-identity elements in each Sylow 5 subgroup. And this corresponds to the number of Sylow 5 subgroups. Okay. Back to the calculation, this would give us 64 elements. Okay. So that means we have 64 elements of order 5. But that means that, so given 64 elements of order 5 and 1 identity element, or actually let's leave the identity element aside for now, we have 80 minus 64 elements, and that's obviously 16, left to be included in Sylow 2 subgroups. Okay? But we know that each Sylow 2 subgroup has size 16. Okay? For one Sylow 2 subgroup. Okay? So what we conclude from this is that when we assume that n5 is equal to 16, that implies that n2 must be equal to 1. Okay? So because we had the options n5 equals 1 or 16, if n5 is 1, then the Sylow 5 subgroup is normal. If n5 is 16, then the Sylow 2 subgroup is normal. Okay, so given either option for n5, we have a normal Sylow P subgroup. Okay, so G is not simple. Cool. Next example we'll see is 160. So first thing we do, as always, is the prime factorization. We have 16 times 10, so 32 times 5, 2 to the 5th times 5. Okay, now let's consider using Sylow's theorem to find n2 and n5. We have n2 congruent to 1 mod 2, and dividing 5. So n2 must belong to the set 1 or 5. As for n5, this is going to be congruent to 1 mod 5, and it's going to divide 2 to the 5th, which is 32. Okay, so what does that tell us about n5? It could be 1, and 6, 11, 16 would also work. Okay, and that's it. Okay, so we have two options for each of n2 and n5. If G were to be simple, we would need n2 equals 5 and n5 equals 16. Okay, so let's consider that situation. Okay, so Suppose n2 equals 5 and n5 equals 16. So counting the elements of order power of 2 is going to be complicated because each CLFP subgroup each CLF2 subgroup has size 32. So instead we'll focus on n5. Okay, so if we have 16 5 subgroups, that means we have 5 minus 1 times 16 elements of order 5. So that's 4 times 16, or 64 elements of order 5. That still leaves plenty of room for the CLF2 subgroups. So 160 minus 64 is 96. Plenty of room for 5 CLOV2 subgroups. Okay, so that's not quite working for us. But let's instead think of possible group actions. Okay, again, and we talked about the possibility of acting by conjugation on a set of CLFP subgroups, or acting on a set of cosets of some subgroup. The set of CLF2 subgroups is only size 5, which is quite small. So let's consider the action that it induces. So we have G acting on CLF2 subgroups of G. This induces a homomorphism from G to the set of to the group of permutations on 5 letters, since there are 5 CLF2 subgroups. And now we want to consider what the kernel of that homomorphism could be. Well, we know that the kernel of any homomorphism is a normal subgroup of your group, and because G is supposed to be simple, it only has 2 normal subgroups, the identity and the full group. Okay, so this could be trivial subgroup or the full subgroup. But we know it's not going to be the full subgroup, because if it were the full group, because if it were the full group, then G would be acting trivially. Okay, so we know by Sylov's second theorem that G does not act trivially, because you're able to conjugate any subgroup into any other subgroup. So that tells us that the kernel must be the identity. Okay. The fact that the kernel is trivial tells me that phi is injective. So we can think about G as a subgroup of S5. Okay? But if G is a subgroup of S5, we have to consider what their cardinalities are. We know that S5 is 5 factorial. And let's get the prime factorization of that. We have 2 times 4 gives us 2 cubed times 3 times 5. Whereas G is 160, that's 2 to the 5th times 5. So it's impossible for us to have 2 to the 5th as a subgroup when the larger group has highest power of 2 cubed. Okay, and this is by Lagrange's theorem. Lagrange's theorem implies that G of order 160 cannot be a subgroup of S5, since 2 to the 5th does not divide 2 cubed. So we have a contradiction, and G must not be simple. Okay. So in particular, where does the contradiction come? Well, when we suppose that n2 could be equal to 5, we get this induced homomorphism to S5, which results in a contradiction. So it can't be that n2 is equal to 5, and it must be that n2 is 1. Okay. Now let's take it further, okay, and this will be the trickiest example. We're considering when n equals 90. Okay, so as always, we take our prime factorization. We have 2 times 45, that's going to be 3 squared times 5. And now we're going to apply Sylow's theorem. So n2 is congruent to 1 mod 2, and it divides 3 squared times 5. So that gives us many possibilities. n2 has to be one of 1, 3, 5, 9, 15, 45. As for n3, this is going to be equal to, congruent to 1 mod 3. So we have, and we also have n3 divides 2 times 5, which is 10. Okay, and that is much smaller set of possibilities. We'll have 1. Okay, and then the other integers that are 1 mod 3 up to 10 are 4, 7, and 10. That means that 1 and 10 are our only options. Okay, and one more is n5 congruent to 1 mod 5, and n5 divides 2 times 3 squared, which is 18. So this tells us that n5 could be 1, or it could be 6. And no other integer satisfies those two. Okay, so this is probably going to be too messy to deal with. Okay, there's just too many options. On the other hand, if we're just looking at n3 and n5, if what we want to discover is that one of these guys is going to be 1, we can prove by way of contradiction by supposing that n3 is 10 and n5 is 6. So let's write that down. Suppose n3 equals 10 and n5 equals 6. Okay, so let's count the elements of each order we would find. Well, one thing to observe is that for elements of the Sylow 3 subgroups, those individual subgroups might intersect each other non-trivially, so counting their elements will be tougher. But for the Sylow 5 subgroups, we can. So let's count those. So for elements of order 5, we're going to have 5 minus 1 such elements in each group, and we have 6 such groups. That's going to be equal to 24. Unfortunately, that still leaves 90 minus 24. So 90 minus 24 is equal to 66, which is still plenty of room for 10 Sylow 3 subgroups and however many Sylow 2 subgroups. Not however many, but some small number of Sylow 2 subgroups. Okay. So what do we do next? Well, let's consider group actions. If we have n3 equals 10, so it's trying to act on that might be not ideal because we'll be working in S10, which is quite large, and you won't run into any contradictions. We could think about acting on the set of Sylow 6 subgroups. So let's think about how that would look. So if we have G acting on, Sylow 5 subgroups, because there are only 6 of them. So G acting on Sylow 5 of G, which is a set of order 6. Okay. So then we would have B from G to S6. And by the same logic as the previous example, we would have that G can be thought of as a subgroup of S6. Unfortunately, in this case, this will be order 90. This will be order 6 factorial. So this is 5 times 2 times 3 squared. This divides into 6 factorial perfectly fine. So we're not going to get a contradiction from Lagrange's theorem in this case. Okay, so we're now going to advance gingerly to step 5, which is to study the normalizers of intersections of CLFP subgroups. Okay, so in this case, we're going to look at the Sylow 3 subgroups. Okay, so we know that N3 is equal to 10. Okay, so there are 2 cases. Case 1, none of the Sylow 3 subgroups are intersect. All of them intersect only in the identity, which means that they're all completely disjoint. Okay, so P intersect Q equals the identity for any PQ in Sylow 3 of G. Okay, in that case, we can count elements again, and we'll find 9 minus 1. Okay, that's the number of non-identity elements in each Sylow 3 subgroup, times 10, which is the number of Sylow 3 subgroups, which will be equal to 80. Okay, and that leaves only 10 remaining elements. For how many Sylow 5 subgroups? It would have to be 6. And so there would need to be another 24 elements. So that's not going to work. Okay, so that tells me that in this case, so this case finds a contradiction, which means that this case is impossible. Okay, so this case leads to contradiction. Now let's consider the next case. So we're considering where P intersect Q is non-trivial. Okay, so because they're distinct groups, both of them have order 9, their intersection could be of cardinality 1, 3, or 9 by Lagrange. But if it was 9, they would be the same group, which would be a contradiction. If it's 1, that's what we already covered. So this intersection has to be 3, of size 3. Okay. And now let's dig a little deeper. So we have 2 subgroups of G of order 9. They intersect in a subgroup, let's call it H of order 3. Okay. Let's consider the normalizer of H. So because both P and Q are of order 9, so P and Q being of order 9, in particular, this is a group of order P squared, and it's a previously proved result in our textbook that this is an abelian group. Okay, so P and Q must be abelian. And that means in particular that all the elements of both P and Q commute with the elements of H. Okay? And for our purposes, that tells us that P and Q are both in the normalizer. Okay? So we have a normalizer. So P and Q, how many elements is that? Well, it's two subgroups of size 9 that intersect in a group of size 3. So it's going to be 9 plus 9 minus 3, which is 15. Okay. And so that means that the size of the normalizer has to be at least 15. We also know that P is a subgroup of Ng of H, and that in turn is a subgroup of G. And so by Lagrange's theorem, the order 9 has to divide the order of Ng of H, which in turn must divide the order of G, which is 90. Okay, so now we can think about what numbers are bigger than 15, but have 9 as a factor and divide 90. Okay, so that means that Ng of H, possible cardinalities would be, let's see, 18, or 45, or 90. But that means that the index of this subgroup is going to be in the set of 5, 2, or 1. Okay? Those are the possibilities. Let's keep this all green, why not? Okay. But now, what we saw before, that trying to have the group action with a set of order 6 didn't work. But now we have a different group action on cosets with 5 cosets. So let's see if that works. So let's have G. Let's consider the action of G acting on the set of cosets of the normalizer of H. Okay. So this induces a homomorphism from G to S5 this time, or possibly S2 or S1, but that'll be an even easier case to think about. And again, the kernel of phi, if it were the whole group, so it would have to be either the trivial subgroup or the whole group. But if it were the whole group, then the group action would be trivial. But obviously, you can, it's going to be transitive. You can multiply through to get any coset. So you can't have this. You must have this. So that tells me that G is a subgroup of S5. Okay. But now, this has cardinality 90, and this has cardinality, and let's spell out what that looks like, 2, 3 squared, 5. On the other hand, S5 has cardinality 5 factorial, which is 2 times 4 is 2 cubed, times 3 times 5. Okay, so I have 2 factors of 3 in the cardinality of G, and only 1 factor of 3 in the cardinality of S5. So Lagrange tells me, by Lagrange, we have a contradiction. So G must be simple. Okay. So this last example is obviously rather convoluted, but I wanted to include it to give you a sense of how sometimes you have to keep grasping for different angles of where to introduce the group action, or where to try and count elements of different orders by examining different groups and different subgroups and how they might intersect. This is obviously not an exhaustive set of techniques, but I think it'll get you started on your way as you try to master more tools for this type of problem. Best of luck.